So we are going to wrap up the remaining afternoon session with my talk and then one other from Andy. And so let's dive in. So aloha and welcome to my talk. So today I'm going to teach you how to analyze the anti-analysis logic of M1 malware. And as we can see on the slide, I'm roughly defining M1 malware. That's malicious code that's been compiled to run natively on Apple's new M1 or ARM64 systems. First, we're going to cover some introductory topics. We'll talk about how to find M1 samples for analysis. However, once we find those analyses, we will first have to have at least a foundational understanding of ARM64. So we'll dive into that and cover that as well. And then once we've been armed with that foundational understanding of this instruction set, we're going to dive into analyzing what was the first publicly discovered Mac M1 malware sample, specifically focusing on its anti-analysis logic. So let's start with some introductory concepts, some topics. First, this is kind of an obvious slide, especially for all of us here. It should be really no surprise that Macs are becoming ever more prevalent, especially in the context of the enterprise. And equally unsurprising, Mac malware is becoming ever more popular, prominent, prevalent as well, basically in lockstep with Mac's growth. Now, on the next slide, we'll dive more into Apple's new chip, the M1, but it's worth pointing out that the argument can be made that it's really driving the increased adoption of Macs. I mean, it's an incredible piece of hardware, and home users and enterprise users are taking note. And this point is clearly articulated by Apple's CEO as well, who notes that, yes, indeed, this chip is driving the growth of the Mac platform. So what is M1? Well, it's also referred to as Apple Silicon. It's an ARM-based system on a chip, or a SoC. A SoC simply means you have a single chip that has multiple technologies combined all on it. So things like the GPU, the CPU, DRAM, which traditionally were disparate parts, now they've been all combined into one chip, which is one of the reasons it's so efficient. Now, in the context of this presentation, this talk, the most important factor is that binaries, including malware, compiled to run natively on this platform, on the M1 CPU, will disassemble into the ARM instruction set versus perhaps the more familiar Intel instruction set. I also want to point out, you might be having the question, why do we need to talk about M1 malware? What's the purpose of this talk? Why should we even care? Well, first, M1 malware is inevitable. Obviously, compiling something to run natively on a platform's CPU is a no-brainer. Native code is going to run faster. Yes, Apple has shipped the M1 systems with Rosetta, which is a translation technology that can allow Intel binaries to run on macOS systems even with the M1 chip. But Rosetta has been prone to some crashes, and there's going to be some speed penalty. Also, I did an interesting study where I took a malware sample that had been compiled both for Intel and M1 or ARM64 systems and uploaded them both to VirusTotal and found that for the ARM-based detections, there was about a 10% drop. So this shows that some AV companies have architecturally specific signatures. So as security researchers, this is something we should be aware of. Mainly, though, we need to talk about M1 malware because it's ARM-based. And I said that means it's going to disassemble into the ARM instruction set. And if we don't understand this newish instruction set, we're not going to be able to comprehensively analyze these samples. First, though, we need to talk about what an M1 binary is, what it looks for, how we can find samples to analyze. Turns out it's really not that hard to detect. First, it's going to contain ARM64 code, obviously. And until M1 is the dominant hardware, the majority of binaries that support M1 code natively are going to be distributed as universal binaries. Universal binaries are simply binaries that contain multiple architectures. So, for example, Intel and ARM. Basically, what the compiler, the linker, does is compile both architectures and then concatenates both binaries into one file. When the user or when that binary is then launched on a system, the dynamic loader, DYLD, decides which is the correct architecture. So on an Intel system, the Intel binary will run. On the ARM64 M1 system, that one will execute. Also, we can check the macOS header to see that indeed these binaries have been compiled to run on macOS. This is important because iOS also supports ARM64. And in this presentation, we're merely interested in M1 malware. So once I kind of gained an understanding of what an M1 binary would look for, I decided to go hunting. I don't have access to customer data, so really the only option I have as an independent security researcher is VirusTotal. And VirusTotal really has done a great job, yes, collecting a corpus of files, but also making available researchers' accounts. So here's the search query I used. My goal was to find M1 malware. We can see based on the tags, the types, I'm looking for a macOS binary. I'm saying type ARM, 64-bit. I'm saying multi-architecture, basically looking for these universal binaries. Using the engine flag saying not iOS. I'm only interested in Mac binaries. And finally, I'm looking for binaries that have already been flagged by at least 2 antivirus products. The idea was, yes, I might miss some brand new malware, but as we mentioned, most malware authors are most likely going to compile their existing Intel malware into M1 binaries and ship them as universal binaries, so I figured that existing AV signatures would likely flag that. So I ran the search earlier this year, and it turned up just a single candidate binary, something named GoSearch22. As we can see on the slide, it's a universal binary. It has binaries for both ARM and Intel-based code. Unsurprising, the malware authors wanted to make sure it could run natively on both platforms. We can also see that looking at the load commands, that it's been designed specifically to run on macOS, so we now know we have an M1 binary. Interestingly enough, Apple had already revoked the certificate for this, and some antivirus engines were already flagging it as malware, likely on the Intel-based code. So clearly it's a shady binary, and continued analysis confirmed it was a variant of the highly prolific Pirate malware family. Rather awesomely, and this is somewhat tangential, I wanted to see how or why this was submitted to VirusTotal. And based on the API information and metadata, I could see it was submitted to VirusTotal by a user running one of my tools, Knock Knock. So Knock Knock simply enumerates persistent software that's installed on the system. It integrates with VirusTotal, meaning users can submit, for example, files they don't recognize. So what happened was, end of last year, a user ran this tool, came across this persistent binary, didn't recognize it, and submitted it to VirusTotal. Then when I did my search in January or February, I stumbled across it as well. Kind of neat. It's also worth pointing out that, as expected, since this initial discovery, M1 malware continues to abound, continues to proliferate. And unfortunately, we have cases where Apple has, in some cases, inadvertently notarized these samples as well. So it's definitely becoming more of a problem, and as is always the case, we can't fully rely on Apple's built-in security mechanisms. So, hooray, we found what appears to be the first instance of M1 malware in the wild. However, before we can dive into it and analyze it, we have to gain at least a foundational understanding of the ARM64 instruction set, as this is what this malware will disassemble into it. Good news, though, we don't have to become experts. Once we have some basic understanding, we'll see that this gets us pretty much as far as we need to go. So now I'm going to dive into some reverse engineering concepts specific to some that are specific to ARM64. So first up, let's talk about registers. If you do any reverse engineering, you're well aware that they are essentially name slots on the CPU. I kind of like to think of them as variables. So ARM64 has 31 64-bit general-purpose registers, uncreatively named X0 through X30. If you want to refer to the lower 32-bit component of these registers, you use the W prefix. So for example, W0 refers to the lower 32 bits of the X0 register. There's also a few dedicated registers that are worth noting. For example, SP is the stack pointer. PC is the program counter or the instruction pointer. And then finally, there's a dedicated virtual register known as XZR, which is always set to 0. There's also some floating point registers, but in the context of malware analysis, those aren't really relevant. And finally, we have the p-state entity, which holds condition flags. We'll talk about this more shortly. Now, during malware analysis, you don't have to understand each and every assembly instruction, right? That's just going to take way too long, and that's often overkill. So what you can normally do is just study the code around API calls, because often this will answer the questions you seek as a malware analyst. For example, you probably want to know, does the malware talk to a command and control server? So you can find the code that invokes various networking APIs and then look at the values of those arguments, right? Is it initializing a URL with an embedded hard-coded address of a command and control server? If so, hooray, you've just uncovered its command and control server. So in reverse engineering code, there are specific rules or a protocol that dictate how arguments are used in the context of a function or method call. And this is articulated in something known as the ABI, or the Application Binary Interface. So knowing these rules helps us, for example, to know exactly which arguments can be found in which registers. In ARM64, the ABI dictates that the first 8 arguments will be passed in registers X0 through X7. If you're coming from Intel, this is kind of nice because in Intel, the registers are kind of random, right? It's like RDI, RSI, RDX, RCX, R8, R9. Like, I have to write this down because I rarely remember it. ARM, it's just X0 through X7. It's awesome. Before entering a function, the return address, which is where the CPU will return to after the function call, is stored in X30, which is also known as the link register. Inside the function, the X29 is used as the frame register, or FP. And then finally, when the function returns, the result of the function or method is going to be found in the X0 register. Unless it's returning a 128-bit value, it will then use the X1 register as well. All right, now on to some ARM64 assembly instructions. Instructions instruct the CPU what to do. Instructions start with something we refer to as a mnemonic, which is just a human-readable abbreviation that articulates what the instruction does. So for example, the add mnemonic is for the addition instruction, really not rocket scientist. The remaining part of the instruction is made up of operands, and of the operands, there are, well, 3 types. First up, we have the immediate operand, which is simply a constant, something like 42. A register operand is simply one of the registers we mentioned, for example, X1, X0. And then finally, you can also have a memory operand, which is a register value that points to a memory location. So it's really just a pointer. One thing to note that almost always the first operand is the destination register. So for example, in this instruction, we can see there's an addition being performed. The result of the addition is going to be stored in X1. So it's going to take 42, add it to X0, and then store it in X1. So you can kind of read it, from right to left. We also need to talk about ARM's memory access model, because unlike Intel, ARM separates instructions into those that can access memory and those that cannot. On Intel, most instructions can directly access memory. So what happens on ARM is you see an instruction that will load a value from memory into one of the general purpose registers. Some operations are then performed on that data in the register, and then when the program wants to store it back into memory, it executes a dedicated instruction to do this. This is referred to as a load and store architecture, and this is what, again, ARM uses. Let's look a little closer at this, because when reversing malware, you'll see these instructions used a lot. So to load something into memory, ARM64 makes use of the LDR instruction, or one of its variants. If you take a look at the example on the slide, as normal, the first operand, in this case the X1 register, is the destination register. The source register is X0. Brackets around it indicate that it's a memory operand, which tells the CPU that it should dereference that value and then go there in memory. So with this understanding, we know that this instruction is loading the value stored in the memory address found in X0 into the X1 register. And we have the analogous C statement as well if you're more comfortable reading something like C. On the other hand, the str or store instruction will store a value from a register into memory. This instruction is somewhat different in the sense that the first operand is actually the source register, while the second is the destination. So this one you kind of read from left to right, right? So it's going to take x1 and store it into x0. Now let's look at comparisons. You encounter comparisons a lot, especially when analyzing malware. It will oftentimes do something like query its environment and then make a comparison to determine what of two alternate code paths it should take. Here we have the comparison instruction that compares two operands and then updates the flag in the p-state entity. Once these condition flags have been set, for example, via the CMP or comparison instruction, subsequent instructions will then act on these flags using something called condition codes. These codes can include things like equal, not equal, less than, greater, etc., etc. So let's take a closer look at the example on the slide, which contains anti-debugging logic extracted from a malicious sample. The logic will cause the malware to exit prematurely if it detects a debugger. Basically, the malware says, I don't want to keep running if someone like Patrick is debugging me. First, we can see there's a compare instruction checking the return value of a function named am I being debugged. If the function returns a 1 or a true, meaning the malware is being debugged, the 0 flag will be set when the compare instruction, compare w01, is executed. And again, remember that the return value from a function can be found in x0 or its lower 32-bit components, w0. The next instruction we see is a BNE. This is a branch not equal. This will skip over the early termination if and only if the 0 flag wasn't set, meaning the function didn't return 1, meaning the malware isn't being debugged. Otherwise, it will exit and thwart our continued analysis efforts. And speaking of branching, let's take a closer look at some branch instructions and variations. First, noting that branch instructions are how ARM64 alters the control of a program. First, we have a B or a BR instruction. This is synonymous essentially to a jump instruction on the Intel platform. Give it an address or a register, it will unconditionally jump to that and continue code execution there. On the last slide, we talked about conditional branch instructions. These are the next type of branch instructions. These will only branch if the condition is met. If the condition is not met, it's essentially a no-op and do nothing, and program control will just continue sequentially. Finally, we have the BL or BLR, which is the branch and link or branch and link register instruction. And what this first does is stores the address of the next instruction in the X30 register, which recall is the link register. Then it will branch. Then when a return instruction is encountered, this will read the value out of the X30 register and jump back to that. So this is how ARM64 performs function or method calls. All right, so now let's put this into action, and what we're going to do is we're going to reverse engineer Apple's Hello World code. If you open Xcode and create a new Objective-C project, this is the code that will be generated. On the slide, we can see the Objective-C code, and on the other side, what it looks like once we disassemble it, the ARM64 instructions. One point to know that during the compilation process, the auto-release memory block is compiled into a call to pool push and pool pop. So first, looking at the disassembly, we have the function prologue. Generally, when analyzing malware, you don't have to worry too much about the function prologue. It simply does things like make space on the stack for local variables, store registers that need to be preserved across a function call, etc., etc. So we're not going to spend too much time there. Continuing on, though, we see a call to the pool push function via the BL instruction, which recall is the branch and link instruction, which is the instruction to make a function or method call. Remember, this function will first store the address of the very next instruction, so when the function executes a return, program control can continue in the correct place. Now, if we read Apple's documentation on this pool push function, we can see it returns a pool object that at a later time must be freed. This means the program's got to store that. So if we look a few instructions down, we can see this return value, which recall is going to be in the X0 register, is stored on the stack via the str instruction, which we talked about earlier. So basically, the function is storing this locally, so at a later time, it can re-access it and free it. Next up, we have the nslog function. This is how you print out something in Objective-C. Again, it's invoked via the bl instruction, branch and link, and it's going to print out the hello world string. Now, the nslog function takes a parameter, specifically the string to print out, and recall that according to the ABI, certain registers have to be initialized with parameters in the correct order. So for a function that takes one parameter, the x0 register has to be initialized with this parameter. So if we look at the disassembly, we can see x0 being initialized with the address of the string to print. The nslog function is then called. It reads the x0 register and prints out our string. The code now leaves the auto release pool via a call to the pool pop function. If we read the documentation about this, it expects a pool object to free. Recall that this was returned and stored previously, so we can see the disassembly using the LDR instruction to load the stored pool object off the stack into the x0 register. Again, x0 is where the first argument is expected. It then makes the function call to free the pool object. Finally, we have the function epilogue. Again, in the context of malware analysis, we don't spend too much time here. Basically readjusts the stack, initializes a return value, and then executes the return instruction to return back to the caller. Now, the good news is, normally we don't have to dive that deeply into disassembly and understand that many assembly instructions, for two reasons. Decompilers now do a pretty good job of taking disassembled instructions and reconstructing the logic back into a representation of higher level language, for example, C or Objective-C. So on the slide, we can see I took the disassembled code and ran it through a decompiler, and it produced fairly readable Objective-C code. A lot more succinct and probably easier to read than the ARM64 disassembled instructions. Also, if you're doing malware analysis, a lot of times you can lean on dynamic analysis tools such as file monitors, process monitors, and debuggers, and those don't necessarily you don't necessarily have to have that deep of an understanding, especially a process monitor or a file monitor. Oftentimes you can simply run a malware sample and via these monitors ascertain exactly what it does passively. All right, so let's now dive into some anti-analysis logic. I just told you that you often don't really need to understand ARM64 or dive into disassembly that deeply. The one time you have to, unfortunately, is when malware leverages anti-analysis logic. Malware authors realize the power of both decompilers and dynamic analysis tools, so what they do is they implement anti-analysis logic to directly thwart these tools and our analysis efforts. So for example, as we can see here on the slide, if we go run GoSearch22, that first publicly discovered instance of M1 malware, we can see it just exits. And this is because, as we'll see, it detects the debugger and exits. This is problematic because we want to continue our analysis. So what you have to do is identify any anti-analysis logic that the malware implements, then bypass that. And once you've identified and bypassed it, you can then fall back to the more powerful dynamic analysis tools like your file monitor or process monitor, which don't require that deep of an understanding of ARM64. But again, you kind of have to get the anti-analysis logic out of the way first. It's also important to note that if we load the GoSearch22 malware, the parent malware, into a disassembler and try to decompile it, it just turns out to be junk. The malware authors have obfuscated the code. I believe they use the public LLVM obfuscator, which adds garbage instructions and spurious function calls. Again, this is just an effort to complicate our analysis and confuse the decompiler. So again, unfortunately, we have to use the disassembler and kind of get down and dirty with ARM64. So we mentioned that this malware executes, or rather exits, if it detects a debugger. We want to be able to continue debugging the sample to extract all its secrets and learn exactly what it does. So we have to figure out how it's detecting this debugger. So reading through the disassembly, we come across these 5 instructions. First, we see 4 registers are initialized for 4 arguments. Then the SVC, or supervisor call instruction, is made. I had to Google this instruction. I didn't know what it was. But luckily, Google, Stack Overflow, very helpful. If we look at the arguments, especially in the context of this supervisor call, we can see that the hex value 1A maps to sys ptrace. So now we know the program, the malware, is invoking the ptrace system call. In the context of the ptrace system call, the value of 1F maps to the pt deny attach flag. If we read up about this flag, we see that when passed to the ptrace function, this tells macOS to terminate an application or a program if it's being actively debugged, and if it's not, prevent a debugger from being attached. So now that we've identified the anti-debugging logic, how do we bypass it? Well, it turns out it's pretty easy. What we can simply do is set a breakpoint on this problematic supervisor call. Then when our breakpoint is hit, the debugger will halt the execution of the malware before this call has been made. We can then modify the instruction pointer to simply skip over the problematic call. And once we do this, we then tell the malware to continue executing, and it's none the wiser. But the problematic system call has never been made. Unfortunately, the malware has other anti-analysis logic. It also checks if it's running on a system that has system integrity protection disabled. Often analysts will turn this off while analyzing malware. So the malware rightfully has made the assumption that if it finds system integrity detection off, it's going to exit because it assumes it's being analyzed. So I was stepping through this in a debugger because we've overcome the anti-debugging logic, and it made this call BLR X8 and just bailed. And I was like, what's it doing here? So unfortunately, from the disassembly, we can't figure out exactly what it's doing. But as I mentioned, since we overcame the anti-debugging logic, we can poke around and see what the values of these registers are. So for example, we can see the X8 register holds the obfc message send function. The obfc message send function is the Apple API that's executed whenever an Objective-C function call is made. Apple documents this so we know what the values of the arguments should be, so we can print them out in a debugger. Here we can see it's an NSTask object, and it's invoking the launch method. Reading more about the NSTask object, we can see it has other instance variables or properties, including a launch path and argument. We can dump these in our debugger. As we can see on the slide, via the arguments, it's going to invoke binsh, passing in the command csrutil, which is how you execute a check to see if system integrity protection is enabled. So the malware is basically delegating out to the system. We also find that the malware employs anti-VM logic. Malware authors rightfully assume that if the malware finds itself running in a virtual machine, it's likely being analyzed. It uses the same obfc message send function, but again, in a debugger, we can print out the values of both the object and the method that's being called, again, seeing it's an NSTask or NSConcreteTask object. And by looking at the properties of this second NSTask object, we can see that it's executing a large script that looks for various virtualization products. So that wraps up the anti-analysis logic of the malware. Given an understanding of the ARM64 instruction set, we were able to identify this logic and then trivially bypass it by manipulating the instruction pointer in the debugger. Once this analysis has completed and once the anti-analysis code has been identified and overcome, we can fall back to the more passive, more powerful dynamic analysis tools like process monitors and file monitors to find out what the malware does. So, a few takeaways to wrap this up. First, we talked about how to hunt for M1 malware. If you pop on VirusTotal and do that same search query we talked about, you'll find a myriad of new malware samples that have been compiled to natively run on Apple's new M1 systems. We talked about how to understand ARM64, at least some basics. This should hopefully point you in the right direction and get you along becoming a proficient analyst of M64 malware. Finally, we showed that in the context of reversing malware, oftentimes you really only have to get that deep into the instruction set when looking for and identifying anti-analysis logic. So again, the goal is really to arm you with these topics today to really set you on the way to becoming a proficient malware analysis, even when analyzing M1 malware. Now, of course, this is in some ways just the tip of the proverbial iceberg. So if you're interested in learning more, there's a great book on the topic. There's also some great online tutorials that have been mentioned. Some of the other researchers I quoted in the slides have some great blogs, some great topics on reverse engineering and analyzing ARM64 binaries and instructions. And in the context of malware analysis, the book I'm writing also dives into this as well. Yes, want to thank the sponsors who sponsored my research in both the talk. So again, thank you so much to all of them. Couldn't do this research in the conference without them. So again, big mahalo. And really, yeah, now go forth. Reverse engineer this Mac M1 malware. It's here to stay, and we need more researchers pulling it apart to keep the attackers on their toes. So that's a wrap. Thank you again for listening to my talk. Unfortunately, I went slightly over, so if there's any questions, hop on the Discord channel or approach me at the party, and we'll talk nerdy about M1 malware. Thanks again.